In this new section, we are going to talk about the equidistant theorems. The first one basically says if 2 points are each equidistant, from the endpoints of a line segment, then something must be true. Then the 2 points determine, you should think about it. What does it determine? Determines the perpendicular bisector of that segment. Now, exactly what is going on here? What is this theorem really saying? 2 points are equidistant from the endpoints of a line segment. So here is a line segment AB. And 2 points are equidistant from the endpoints. Say this point and that point. What does that mean? Well, call this point C and D. The distance from C to A and C to D, they are equal. Excuse me. But the 2 points are equidistant not from a endpoint, but from their endpoints. That is, this distance and that distance, they must be equal. Okay, so that's what the if part says. Then it says the 2 points determine the perpendicular bisector. Okay, now my graph is off a little bit, but when you connect this, what it's saying is it meets at a right angle, and those two sides are the same length. Okay, if 2 points are equidistant from the endpoints of a line segment. So let's do this again. This is important. So you have a line segment, and I pick 2 points that are equidistant between both ends of that line segment. That is, this distance and that distance are equal, and also the other endpoint from these 2 points, P1 and P2, that are same distance to B. If that's true, let's call this A. If that's true, if you were to connect P1 and P2, you would discover that that is P1E and P2E, those are the same lengths, and it's perpendicular. That's what the theorem says. And that's another piece of ammunition that we can use. To prove theorems. Now, there's another theorem. It's basically maybe the converse. Think about it. If a point is on the perpendicular bisector of a segment, then something is true. Well, then it is going to be equidistance to the endpoints of that line segment. The endpoints of that line segment. What is this saying? You have a line segment, and you consider the perpendicular bisector. That is, you go dead center and you draw a line where this length and this length are the same. Okay. Well, actually, that's not even true, but fine. If you pick any point on the perpendicular bisector, well, I picked 2 points. If you pick any point on the perpendicular bisector, that distance and that distance will be the same. It's basically the mirror image. Doesn't look like I picked the center too well. Okay? But if you think about it, this line splits AB right in half. Okay? Actually, those two are supposed to be equal. I'm sorry. AC and BC. Now, if you were to fold a piece of paper along that line, point B would go right on top of point A. In fact, this whole line would go right on top of that line. Now, if I folded along that line, that wouldn't be true. But since that's a perpendicular line, it is true. So we have symmetry. This point is as far as the distance from D to A. It's as far from A as it is from B. That's all that theorem is saying. And that makes pretty much sense. And to prove it, it's a pretty easy proof. Because we're given the right angle. So now we have 2 triangles, one on the left, one on the right. And what do we know about these 2 triangles? Well, we know that AC in triangle 1 and BC in triangle 2 are equal. And CD equals itself, and that's in 2 triangles. And they both have a right angle. So by side, angle, side, these 2 triangles are the same. So their corresponding parts must also be congruent. Okay, so that's our second theorem that you can use to prove things in this section. So let's go ahead, try to prove a couple of things. The first one is you're given a circle O. And M is the midpoint of AB. Should have drawn the picture first. And you want to prove, you want to conclude that OM is actually perpendicular to AB. And how do you do this? Well, let's have the picture. You have the circle O, and you have some line segment AB, and it clearly says that M is the midpoint of AB. M is the midpoint of AB. And you want to show that OM is perpendicular to AB. Well, statement, reasons. The first statement is the givens, and the reason is it was given. Okay, so basically we know that AM and BM are equal because M is in the middle of AB. All right. Now, if we were to draw AO and AB, well, these are equal to one another. These are equal to one another. AO is congruent to BO. Well, let me not say that yet. AO is a radius for circle O, and BO is a radius. Why is that? A line that goes from the center of a circle to a point on the circle is a radius. 100% definition of radius. Number 3. Now I can say they're equal, or congruent if you prefer. All radii are equal. Okay. And of course, OM is congruent to OM. Identity. Okay, so S and R's, we now can say that the triangle to the left, that is triangle AMO, is congruent to triangle BMO. By side, 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 it's congruent to side, side, side. Okay, so let's call this angle 1, and let's call that angle 2. Number 6. Angle 1 is equal to angle 2. Corresponding parts of congruent triangles are equal. Number 7. A and B is a straight line. Remember, A and B is just AB. A and B is a straight line. And the reason is all line segments are straight. Okay. Angle M is 180 degrees. All straight lines equals 180 degrees. Now, angle 1 plus angle 2 is M. Let me get rid of this, please. angle 1 plus angle 2 is M. Angle 1 plus angle 2 is M. Sum of parts equal the whole. Okay, some reason this didn't come out. Angle 1 plus angle 2 is angle M. Right. But angle 1 is angle 2. I should be saying the measure of angle 1. So, 2 times angle 1 is angle M, which is 180. 2 times angle 2 is 180. Basically, instead of angle 1, I'm calling it angle 2. Angle 2 plus angle 2 is 2 times angle 2. Okay, and the reason is angle 1 equals angle 2. Okay, now I divide both sides by 2. Angle 1 equals 90 degrees. Angle 2 equals 90 degrees. Division property. Number 12. Angle 1 equals angle 2, which equals a right angle. All 90-degree angles are right angles. All right. Now the perpendicular. If angle 1 is 90 degrees and angle 2 is 90 degrees, MO must be perpendicular to AB. OM is perpendicular to AB. Why? Right angles only perpendicular lines meet at right angles. Only perpendicular lines meet at right angles. Okay, so there's the proof. It was a bit long. It probably could have been done shorter. Okay. Let's try another one. Here's a diagram. You have W, say X, point Y, and point Z. And you're given some things. You're given that WZ is the perpendicular bisector of XY. Is given. That's given. And you're also told, and actually that's all that's given. And you want to prove, here, that's all you need. You want to prove that triangle WXY is isosceles. Now, all you know is that WZ, now I don't buy what I wrote. Yeah, we just need to switch the letters. X, Y, Z. WZ is the perpendicular bisector of XY. That is, these two are equal, and it's perpendicular bisector. Now, WXY, triangle WXY is the big one. Now, all you want to do is show that they're isosceles. Well, it's done. It's done. Those two are equal. Okay, that's exactly what theorem number 25 said. It says, if a point is on the perpendicular bisector of a segment, here is the segment WZ. Here is the point, here's the line segment WZ. And W is any old point. And it's on the bisector. I mean, VW could have actually been extended in theory. Okay, if W is any point on the perpendicular bisector, then W is equidistant from those 2 points. That is, these two line segments are equal, and we're done. WXY, triangle WXY is isosceles. It had 2 equal sides. Okay, so statement and reasons. I purposely put it down here in this small area because I think that's enough givens. And what's the reason? It was given. And number 2 is triangle. Okay, that's not true. I think it's going to take 3 steps. We are now going to say that XW is in fact congruent to YW. And the reason is, if a point lies on the perpendicular bisector of a line segment, then this point is equidistant from the endpoints of the line segment. And if in your book this is theorem number 212, you can just say the reason is theorem 212. Now I'm going to say is that triangle WXY is isosceles. And the reason is it has 2 equal sides. Triangle WXY has 2 congruent sides. That's enough for me to call it isosceles. Done. Okay, using this theorem really helped. The last proof, I didn't use one of those theorems, actually on purpose, to show you that you don't have to use it, but also to show you how much longer it is because we didn't use it. Okay, let's try another one. Suppose you are given a diagram like this. Okay. A, B, C, D, and E. D, and E. Okay, and here is what we are going to be given. We're given that AD is the perpendicular bisector of line segment BC. And now we want to prove or conclude the following. That triangle ABC and ACE, triangle ABE, and ACE are in fact congruent. So basically, this triangle up here and this triangle on the other side, they're the same. Now, what do we know? AD is the perpendicular bisector of BC. That means BD and CD are equal. And we have a right angle. Okay, so statement, reasons. First statement always is what you are given. Call it the givens. And the reason you're allowed to have that, the reason why it's true, it's given to be true. Okay. So now I'll say that BD is congruent to DC. In case I need that. Perpendicular bisector splits a line segment into two equal parts. Okay. Now, I claim that AB and AC are the same. Why? Because point A, I don't care if it's an endpoint or not. Point A is on the perpendicular bisector of this bottom line. This bottom line, A is on the perpendicular bisector. This here is a perpendicular bisector. Okay? Point A is on it. Therefore, A is equidistant from the endpoints. AB is congruent to AC. And the reason is, if a point is on the perpendicular bisector, if a point is on the perpendicular bisector of a segment, then that point is, we'll call it ED, equidistant from the endpoints of the line segment. Right. So now, in terms of these two triangles, let's see what we know. We have this triangle here, and then we have the one to the right. And basically, we have that two sides are equal, one that has that V shape and one that has the double slash, and it's a right angle. Okay, and you know, you can now say that AD equals AD if you want. Statement, reasons. AD is congruent to itself. Well, of course that's true. It's identity. That's the reason. It's the same. Identity property. And now, I can say that triangle ABC is congruent to triangle ACE. And the reason, this should be 4, and the reason would be side, side, side is congruent to side, side, side. Of course, we didn't have to state number 4 because we have a right angle. Both triangles are right. I should state that somewhere. I never said that they were equal. Oh, I didn't have to because I have side, side, side. So I can state that those two angles are right. And once I had the hypotenuses equal and one of the legs equal, I can say the triangles are congruent by hypotenuse legs theorem. But that, I think, was more wordy because we would have actually had to say that those two angles on the bottom by point D were in fact right angles. But I got around that. I didn't use the HL theorem. I used SSS. It's congruent to SSS. Okay, let's try one more. That would be it. Have a diagram like such. And we will label, let's say, A, B, C, D, E, F, D, E, I'll call that F, and this G. And we are given some information, and we want to prove some other information. Or we want to prove some other facts. And I rather quickly just want to see something. Okay. Now, we're given, say, that AG is a perpendicular bisector of BC. And we are also told that AG is a perpendicular bisector of DE. And we want to prove that D, I'll call it B, BD is congruent to CE. Okay, so what's going on here? We are told that AG, which is this long side, is the perpendicular bisector of BC. Okay, that means those two halves are equal. That made up, both of them made up BC, and they're equal, and they meet at right angles. We're also told that AG bisects another line segment. It bisects DE into two equal parts, DG and EG. And again, we have a right angle. Okay. Now, we want to prove that this length, DB, or BD, and CE, those are the same lengths. And here we're going to use the subtraction postulate. I'm going to prove that. Now, I can prove that AB and AC are congruent. And the reason is, again, GA can be even longer. Point A, now point A is on the perpendicular, point A is on the perpendicular bisector of BF. Oh, you mean the distance from A to B and A to C are equal? Yeah. And I'm now going to show that these two are equal. That is, AD and AE point A is on the perpendicular bisector. Point A is on the perpendicular bisector of DE. That means point A and D, the distance from A to D, and A to E are equal. Well, if two quantities are equal, like AD and AE, and you take away equal pieces, like AB and AC, what's left over is equal, which is BD and CE. Okay, so let's write that up and we'll be done. Statement, reasons. 1, you have all the givens. Why is that correct? Because you were given it to be correct. You were given. Why is AG the perpendicular bisector to BC? It was given. Okay, so number 2. I am going to say that AB is congruent to AC, and DA, let me call it AD, AD is perpendicular to, congruent to AE. And again, the reasons are, if a point is on the perpendicular bisector of a line segment, then that point is equidistant from the endpoints of that line segment. And I'm not going to keep writing that. But again, if a point is anywhere on the perpendicular bisector of a line segment, then it is equidistant from the endpoints. Again, if here is a line segment, if you go to the middle and you go out, if you pick any, so that's the perpendicular, this long line is the perpendicular bisector of AB. If you pick any point on the line, the distance from that point to A, one of the endpoints, and point B, the other endpoint, these two are the same. Even if you pick another point, that distance, and that distance, they're the same. They're always the same. Now, what I would say for statement number 3 is that AD is equal to AB plus BD. The sum of the parts is the whole. And I'll say the same thing for AE. It equals AC plus CE. I'm just going to call them both statement 3, sorry. Reason: the sum of the parts equal the whole. Alright, now number 4. I'm gonna do subtraction. Remember, AB and AC are the same. That's going to be step number 5. Statement number 4. Remember, AD and AE are the same. That is, these things are the same. Therefore, the right sides are equal. AB plus BD is congruent to AC plus CE. If two quantities are equal, then other things that equal those quantities are equal. This and this. If two quantities equal the same, these are the same. It says it in statement 2. If two quantities equal a third quantity, then those two quantities are equal. If x and y, two quantities, both equal the number 7, you can conclude that x equals y. Okay, number 4. If two quantities equal a third quantity, then these two quantities are equal to one another. Okay, statement number. So now I'm going to take away, remember, AB and AC are the same. I'm going to take them away from both sides. And then BD, line segment BD, and CE are congruent, which, by the way, is what we wanted to prove. And now the reason is, if you subtract equals from equals, the results are equal. If you subtract equals from equals, the result is equal. Okay, that's that one, and that's going to finish this section.